just vector bundle map. So some structure like this. So you take the tangent bundle of this smooth manifold, and at each tangent space, you introduce a map of that tangent space. So these are the canonical projections of this diagram commute. So it just means that every tangent fiber here goes to the same tangent fiber. Okay, there's this vector bundle map J. Okay, that's kind of the trace. That's going to be how the fact that this Y underline comes from this complex manifold Y is encoded. And this satisfies some properties. So satisfying okay. So the first condition is that for every tangent space, for every Y inside my Y underline, the square of the vector, just the linear map associated to that tangent space should square to minus identity. Okay, so this is, maybe I do it like this. So JY, let me say it like this, just to be even more clear. So this is a map from the tangent space to itself. Okay, and satisfies the property that its square is equal to minus the identity. So it's kind of like I squared is -1. That's this is coming from that. And the second thing that this satisfies is that J, what's called integrable. Okay, so I can always just take a smooth manifold and consider a structure like this, where I multiply its tangent space. I introduce this operator for each tangent space such that it squares to -1. And the reason that, the fact that it comes from an actual complex manifold will be will result in this property, which is called J being integrable. And just to write what this means that the Nijenhuis tensor, with some particular tensor, Nj, okay, there's a formula for this guy, Jx, Jy minus J, Jxy minus Jx, Jy minus Xy, I think. Okay, and this should be 0 for every smooth vector field X, Y. Okay, so whenever I input two smooth vector fields on my manifold Y underline, this complicated thing that I write here should be 0. Okay, so my claim is that a complex manifold is equivalent to this data satisfying these two properties. Okay, and this is actually a tensor. It's not important for us. I'm not going to kind of dwell on that, but you can think about kind of how would you phrase that and so on. Okay. Okay, so now one thing that I want to kind of spell out even more is that one direction of this dictionary. So start from Y, and to get from it a Y underline comma J. This is a simple procedure. So how do you do it? So as a topological space, Y underline is just Y. Okay, you have the same space. And then what you're supposed to do is to kind of take this holomorphic atlas and use that to get a smooth atlas, which is of course very easy because holomorphic maps are smooth. Okay, so let me do that. So if Z1, Zn are complex coordinates on Y, then I'm going to be brief. And then we can use x1, y1, dot, 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 x and yn, where zi is equal to x. Well, I is not very good. Zj is equal to xj plus I yj as smooth coordinates. Okay, so these holomorphic coordinates are defined in some open subset of Y. And in that same open subset, I can introduce these smooth coordinates, and the corresponding transition maps will be smooth. So I get a smooth manifold. Okay, let's just the first part of this. And how do I obtain my operator J, this vector bundle map J? Well, so we get a smooth atlas. Okay. And in these special smooth charts, you define J of d dx j. Well, okay, whatever letter I use, it causes a problem. But it's a capital J and a little j, so it's okay. Maybe. Okay, so it satisfies the operator is defined to take this vector, this tangent vector to this tangent vector whenever it's defined. So on this coordinate chart. And I also want g squared to be -1. So I'm forced to define d dyj minus d dxj. Okay, so then these glue together, you can check. So I define something on kind of each special chart, but you can check that by the virtue of being holomorphic, so satisfying the Cauchy-Riemann equations, these things actually glue together. And you actually get this operator to match on the overlaps. Okay. And we also get that the Nijenhuis tensor vanishing. Okay, again, you have to check this, but it's not hard. The hard direction is to go the other way. If you start with some y underline j, where j satisfies these properties, it actually comes from a complex manifold. That's a more difficult thing to do. Okay. So now, why am I saying this? So when you talk about symplectic geometry of complex manifolds, something like taking Kähler structures and so on, I think this viewpoint, instead of thinking about y with its holomorphic coordinates, thinking about this y underline with its smooth coordinates and this j sometimes becomes easier. Okay. So whenever someone gives you a smooth, complex projective variety, you can think of it as a real manifold with this j. And there is this extra condition, which is kind of completely decoupled from most things that you talk about in symplectic geometry, where j is integrable, okay? Which says that j is integrable, but this sometimes can be actually, it's not necessary for symplectic geometry sometimes. You can even relax this. Okay. Okay, so now let Y be a complex manifold. Okay, so a Kähler structure on Y is a Hermitian metric on the complex tangent space so T, I'll just write C just so that you don't get confused. So it's the tangent space of the complex manifold. And what is such a gadget? It's some H, okay, and you input to this H two tangent vectors at the same point, okay, and it gives you a complex number, and it satisfies a bunch of properties certifying that it's Hermitian. Okay, so it's I will skip these properties, but you can write it as J. Not just Hermitian, it's also a Hermitian metric, right? So it's not just a Hermitian form. A certain positive definiteness properties. Okay, so you can now decouple this complex valued thing into its real and imaginary parts. Omega EW. Okay, and what we're seeing here is that this is a Riemannian metric. Okay. Riemannian metric. I'm going to explain exactly on what. And this guy here is skew symmetric. Okay, maybe I used the board a little bit bad. Maybe I put this here. Okay. Maybe. Riemannian metric. So now, in order for me to be able to call this Hermitian metric a Kähler structure, I need a property, which is this property, such that d of omega is 0. Okay, so now this d here is the de Rham differential, is the exterior differential. So I need to make a little note to tell you in what way is this w kind of a real valued smooth differential form. And that's obvious because I defined this y underline thing, and its tangent spaces, which are real vector spaces, are canonically identified with the complex tangent spaces of the y. So you just think of omega here is real two form on just a smooth two form on y underline. And this Riemannian metric, you should think about it the same way. It's a Riemannian metric on this y underline, okay? Where these, what my inputs are identified with tangent vectors of the tangent bundle of y underline. Okay, maybe I write that using the canonical identification T star y with T underline. Okay, so then I get this skew symmetric form. It's closed, and it's also non-degenerate, which is also something that follows from this whole H thing being a Hermitian metric. Okay, so this omega is a symplectic form. Okay, let me write that. So just get this here. So then, symplectic form on y underline means it's a closed non-degenerate two form. Okay, so now this viewpoint of thinking about a Kähler structure, I find extremely confusing to think about because it has a lot of redundant structure. Like this G thing actually can be computed using the data of omega. Okay, so this G, if you follow through these properties, G is something that can be just computed from omega. So omega actually determines everything. Okay, so now using this previously introduced viewpoint about thinking about complex manifolds as real manifolds with this J, I can think about Kähler structures also in a much simpler way. Okay. But at least it's much simpler to me, okay? So it's easier. to think about a Kähler structure via, J to J underline G. I mean, you notice I already had to kind of make contact with this underlying smooth manifold. The reason is that this is not really a holomorphic object. Okay, this is a Hermitian metric. It's not really holomorphic in a way. Okay, so the holomorphic coordinates are not really kind of, it's not. You could understand that maybe using real coordinates could explain a little, could make things a little bit more understandable. So, what is it? It is a symplectic form on Y underline J such that omega J. So now I can define this guy, which eats two tangent vectors again at every point. Okay, and this thing should define for me a Riemannian metric, such that is a Riemannian metric. Okay. So what does it mean for this guy to be a Riemannian metric? Let's spell it out. Okay, so this means i.e. Omega V J W equals omega W J V. So the symmetric property of the Riemannian metric. Okay, and this is equivalent to J preserving omega. Okay, so this condition is equivalent to, you input two vectors into the symplectic form, you get out a number, and then you're supposed to get the same number if you apply the symplectic form after applying J to both of the vectors. Okay, so that's one condition. And the other condition is that omega J V J V is supposed to be positive for every non-zero vector. Okay. So now, I mean, you can of course always think about a Kähler structure in this way. But my point, and if you're seeing it for the first time, you might find it easier to think about it in this way, where you equip this pair J underline Y underline J with a symplectic structure, and the fact that kind of I get a Riemannian metric out of it, which was also the case here, is a condition rather than something that comes out of some manipulation of conditions. Okay, so that's what a Kähler structure is. And let me just say again, so this, if you start with Y comma H, you get Y underline, and this is clear. So this passage is clear. Okay, we already explained how to go from Y to Y underline J, and H gives you omega by that formula. Okay. And another thing I want to say about this. A remark. So again, integrability of J is decoupled from all the other properties. Okay, so I could just have the same structures, y bar, j, omega, assume that omega and j combined in this way gives me a Riemannian metric and so on without j having to be integrable. So I can remove that assumption. And another thing is that if the tangent spaces to a submanifold, so Z inside Y by J is closed under J, then the corresponding subset of Y is a complex submanifold. Okay, so I have some, I have some Y, which is also Y bar as a topological space. Inside this, I take some Z, okay, a submanifold, a real submanifold, and I assume that the tangent spaces to Z, so inside, here I have this entire tangent space of Y underline, and I have this J operator on it. If this subspace coming from the submanifold Z is closed under J, okay, then it's actually a complex submanifold. Okay, it's of course you can restrict J here and get what I will define as the almost complex structure, but it's not just almost complex structure. This Nijenhaus tensor, this integrability condition is also automatically satisfied. Okay. Is there anything? So maybe I make a little definition here. It's not going to be used, but just fine. If M is a smooth manifold, and J Tm to Tm satisfies J squared equals minus identity like before, then Mj is called an almost complex manifold. I'm not going to use this, it's more like a remark, but it's a definition that you can make. Okay, so many things like finding an omega and J compatible in this form, etc., doesn't rely on J being integrable. So you can actually work with almost complex manifolds and almost complex structures too, sometimes. And this says that if you start with a complex manifold, so Y underline J, where you know J to be integrable, then actually almost complex submanifolds are already also integrable. Their almost complex structures are also automatically integrable, in case you cared about that. Okay. Okay, so now I want to do some examples. Any questions so far? So I'm a symplectic geometer, right? So for me, complex manifolds are most important because they give very interesting examples of symplectic manifolds. Okay, and if your viewpoint is that, then this becomes very natural to think of them like this. And the reason why I think even if even if you're not a symplectic geometer, you might want to start at least thinking of it this way, thinking of, for example, Kähler structures this way, is because this Hermitian metric has a lot of structure. And that structure is not, some of parts of that structure are determined from each other, which is kind of only you realize after the fact. So this is kind of the essential piece of data. And it's called the Kähler form. Okay, so this omega is called the Kähler form. Okay, so now some examples. Okay, so the main example is Cn. So Cn is a complex manifold in a natural way, and it gives rise to a real manifold with this operator J. I just wrote the formulas, and I mean that I wrote the local formulas, which are all the formulas here for defining the structure. And here you can take a Hermitian metric, which does this. Cj, and it's just delta ij here. Okay. And if you input the same vector, the same basis vector, standard basis vector, you get 1, otherwise you get 0. But if you kind of then write really what this is in for general vectors, which you can write as j, dj, dj, and you get the sum of cj, dj bar. Okay, so it looks very simple here, but actually, if you wanted to evaluate it on general vectors, it has this expression, which is kind of complicated. You're doing a complex multiplication. Okay, so it's not so easy. And then you can work out from this the induced Kähler form, the induced Kähler form. In real coordinates is just some constant, real constant that I don't want to compute, dxj wedge dyj from j equals 1 to n. Okay, it's the standard symplectic structure on Cn. So C has a symplectic structure where you kind of put dx, ddx, and ddy, and when you input that into the symplectic form, you get 1, and everything else is 0. And then you take the product symplectic structure. Okay, so this formula, this Hermitian structure on Cn gives rise to this Kähler form. Okay, so you need to compute that. Okay, so this is an example, and it's a very important example because then you can take Cn and you can take any of its complex submanifolds and restrict this structure to that complex submanifold and obtain another Kähler structure on that submanifold. Okay, I'll say that, but just so that you don't think this is just some random example. It's not. It gives rise to many Kähler structures by looking at submanifolds. For example, affine, complex affine varieties, right? These are kind of solutions of polynomial equations in Cn. And if the solution set is smooth, then you can restrict this Kähler structure and you'll get a Kähler structure on that affine variety. Okay, but there is another example, which is again kind of a very important example because most Kähler structures that you care about kind of can be obtained from this one. Many Kähler structures can be obtained from this one, again, by looking at submanifolds. So CPN, okay, so this is the complex projective space, has what's called the Fubini-Studi Kähler structure. And I will only describe its Kähler form. So I'll think about CPN underline, and I'll just define the relevant symplectic form. Okay? So consider Cn+1, okay, with its standard scalar structure, symplectic plus Riemannian, I will say, plus Riemannian structure. Okay, so Cm+1 is R2m+2, and there is the flat inner product dot product metric there. That's the standard Riemannian form, and the symplectic form is just what we wrote here. Okay, so then let's call this one omega standard and this one G standard, in case we need to refer to them. And you consider S2n+1 inside C+1, the unit sphere. Okay, so I just take the unit sphere with respect to the standard Riemannian metric. And I know that Cpn is nothing but a quotient of this unit sphere by a circle action. Okay, so which circle action? So U1, the circle, acts on S2m+1 by the diagonal matrices. Like e to the I theta, 0, 0. So it just multiplies every coordinate by e to the I theta. Okay, and you can see that that's an action on Cm+2, but it descends to the unit sphere, preserves lengths. Okay, and then by definition, so Cpn is the kind of set of lines, so one-dimensional complex lines inside Cm+1, which you can also think of by intersecting those lines with this unit sphere as these particular circles generated by this diagonal action. Okay? Okay. Okay, and Cp and just I'm being pedantic, Cp and underline is just by definition equal to S2m+1 modulo this action of U1, which is what I just said. Okay, so now let's try to understand the tangent spaces of this quotient. So this is a free action. I can take the quotient. It's going to give me a manifold. I'm using that manifold structure. Okay. So if I take the tangent space of an orbit inside Cpn, okay, what I'm gonna, so I have this kind of, okay, it's difficult to draw a picture. I'll try. Okay, so here's use a different color. So here's my unit sphere, which is wrongly two-dimensional, supposed to be odd-dimensional. Okay, and you take one of these orbits. Here's my P. Okay, so U1 action is rotating this P around this sphere. And points of Cpn are just these orbits. Okay, and this tangent space to such a point of Cpn can be identified canonically with the perpendicular to this orbit inside S2m+1 with respect to the standard metric. Okay, so this is the G orthogonal inside S2m+1. Okay? So then I write this as, this is equal to Tp U1 P symplectic orthogonal, metric orthogonal with respect to G. Okay, so I have a metric on Cm+1. It restricts to a metric on S2m+1. I have this orbit. At every point to that orbit, I can take perpendiculars. And you can compute that when you take the quotient, these directions die, and what's left is this perpendicular directions. Okay. So now, this guy over here is closed under J standard. Okay, so there is a J. This is a subspace of C and the tangent spaces of C m plus 1. And this one you can check is actually closed under J. Okay, because there's this radial direction which is mapped to this direction of this orbit, and everything else is in this perpendicular. So the J that I'm going to get from the standard structure of CPN is induced from this J, from these slices. Okay, and it's also invariant under U1 action. Okay, so I have all these tangent spaces here, and that's all of these tangent spaces are sent to each other by the U1 action. Okay, so then what I want to do, so what I wanted to get, so I have my J here now. I also want to get a symplectic structure. Right, so the symplectic structure is again going to be induced by the standard symplectic structure on Cm plus 1. So here's what I want to do. Finally, you just restrict the symplectic structure here, the standard symplectic structure on. It's not a symplectic structure anymore. Okay. It's not a symplectic structure because it's not degenerate. And in fact, if you pair any tangent vector with a vector that's tangent to this orbit, it will give you 0. Okay, so that's the kernel of the symplectic form. And because of that, this symplectic structure on the S unit sphere will descend to the quotient and give you a symplectic structure on the quotient. Well, it will give you a 2 form on the quotient, which you can check to be a symplectic form. It will be automatically closed and non-degenerate. Descends to 2 form on CPN underline, which is compatible with J. Okay, so I also, there are 2 ways of getting you can take the standard complex structure coming from the CPN underline being identified with the usual CPN, or you can take this, define it using this description of the tangent spaces. They are the same J. And this symplectic structure that I get is compatible with this J in the sense that when you combine them, you get a Riemannian metric. Okay, so there was one thing that I didn't show here. I actually claim that I said many things, and these many things combined together prove everything that's written here, except one thing, which is that this is supposed to be also closed. So how do I prove that this omega that I get on CP and underline is closed? Okay, so there's a very nice way of seeing this, and I want to just sketch that. Okay. Okay, so here's what you do. So we have sketch of d omega equals 0. Okay, here's how it goes. So this omega is invariant under the UN plus 1 action on CPN. If you want underline, if you don't want underline, it's okay. So why is that? So UN plus 1 acts on CM plus 1, the standard action of the unitary group, and it preserves all of these structures: omega standard, G standard, J standard, everything is preserved. Because of that, when you look at the action, the induced action on the quotient, so UN plus 1 acts on the sphere, and then you can induce an action on the complex projective space. And this omega, because of its construction, will also be invariant. Okay, so this means that d omega is also invariant. Okay. And then here's the key point. There exists an element of um+1. So for every x inside my CPN, there exists an element A which fixes x and acts as minus identity on its tangent space. Okay, you can find such an A. It's an exercise. And this is, if you can always, these things have a name, they are called symmetric spaces. Okay, so, but then what we get is that because this d omega should be preserved under each of these actions, action by A, then what are you doing? It's just you're negating each vector, and it should give you the same result. But because it's a 3 form, that's not possible. Okay, so this d omega takes in 3 vectors, each of which you're negating. So the result is to negate the total result. Okay. Fixed in an odd number of vectors. Okay, so you take in an odd number of vectors. It should be preserved by this action, which gives you this, which tells you that the omega should be 0. Okay. So this is kind of the geometric way of thinking about this Fubini-Studi metric, Fubini-Studi form. You can just write formulas too, and there are many different ways of thinking about it. Okay. So now I want to give you more examples. Okay, so I already said this, but let me say it again. Any J invariant submanifold of a Kähler manifold is also a Kähler manifold with restriction via restriction of structures. Okay. So now let me give you sub-examples of this example. So one, smooth, complex affine varieties, for example. What is a smooth complex affine variety? It's something that's given inside some complex affine space by polynomial equations, and it's supposed to be smooth. But note that there's not such a unique presentation. You could present the same affine variety in as a 0 set of a bunch of polynomials in many different ways. Okay, so when you say a complex affine variety, it doesn't, that structure of an embedding into the affine space is not included. Okay, so as much as you can, you would like to produce structures which are independent of such an embedding, and only kind of depends on the abstract underlying affine variety. Okay, so what we can do is can choose embedding y into Cn, let's make it capital, and restrict. And you can make them Kähler manifolds. But as I said, there are various embeddings, and you don't want to get kind of, you don't want this structure to depend on the embedding. Well, of course, it will depend on the embedding. The details, the exact forms will depend, but up to some equivalence relation, they will not depend. And I'll write kind of the first statement that was proven along these lines. This is a theorem of Chromo and Eliasburg. It says any two such embeddings give rise to symplectomorphic structures, not preserving J. Okay, so what they say is you do this in two different ways. You get two different symplectic structures. And these two symplectic structures are actually symplectomorphic to each other. So you can find a diffeomorphism of Y underline such that one symplectic structure is pulled back to the other symplectic structure. Okay. So so that, for example, so what you can say is the resulting symplectic structure is unique up to symplectomorphisms. And any symplectic construction that you make should be invariant under symplectomorphisms. So there's this uniqueness theorem. And I should also remark that their theorem is more general, and it concerns what's called Stein manifolds. And that's really the right way to think about this statement. You really should think about these as Stein manifolds. But since I don't want to introduce that, this is all I will say. Okay. I'm going to come. So the second thing is smooth projective complex varieties. Okay. So again, because projective means that this a variety that you have can be embedded into projective space. That's what it means. But again, there can be many different embeddings. Okay, so you pick one, and restrict. Okay. How about uniqueness now? Okay, so now there is something so unique. So it's definitely not unique. Not even in this slightly relaxed sense. Okay, but there is a statement, and here's the statement. So what you have is, so you get from this, you get an omega scalar form on Y. And once you have a scalar form, which is just a closed two form, which is in particular a closed two form, you can take its Theorem cohomology class. Okay, so this gives you a class in the second Theorem cohomology of my Y underline. Okay. So this class, if you have two symplectomorphic structures, okay, let me just write down the statement. Okay. So this class is, what I wanted to say is, I think I was going to say something wrong. So this class is an important kind of gadget that you get out of a scalar form. It's its kind of topological counterpart. Topological shadow, maybe. Okay, so it's form. It's just class. It's cohomology class. And now let me write the theorem. So theorem let W1 and W2 be two symplectic forms obtained on Y in this way. Okay, I do this. I take two different embeddings. So, by the way, let me also add one more level of one more flexibility. So, if I have a Kähler form here, I can also multiply that by a positive real number. Okay, see. Well, okay. So that's also a Kähler form. Okay. So I'm allowing for that flexibility here. Okay. Then the classes of these two symplectic structures are the same. There exists diffeomorphism phi, right? Y diffeomorphism such that phi pullback omega 1 is equal to omega 2. The same statement. Okay. All I have to know in order to conclude the same thing is that they have the same cohomology class. Okay. So this theorem is actually easier than this theorem. So the key to this theorem is it's a Moser argument, but the key is that you can interpolate between these two. So if you consider T omega 1 plus 1 minus T omega 2, these are all compatible. So T here is between 0 and 1, are compatible with my J. Okay, so I'm still considering a complex manifold, so there's still this J lying around, right? And whenever I'm taking an embedding, this is a holomorphic embedding. Right? I mean, if you represent something by zeros of a polynomial equation, that gives you a holomorphic embedding. Okay. And so now, when I consider something like this, I know that W1 and W2 are both closed, so any convex linear combination like this will always be closed. But the issue is that it might fail to be non-degenerate. And here, because I have that both of them are compatible with J, then you can check that these convex linear combinations are also compatible with J, which proves to you this non-degeneracy. You can check that for each omega in this family, omega V, JV is positive. So you get non-degeneracy. And then there is this thing called the Moser argument. And Moser argument, if you go and read it, will require that the cohomology class in this family to be constant. But that's just a consequence of the fact that these two are in the same cohomology class. So if I take cohomology, then it will just give me that same cohomology class back. Okay. Okay, so again, this choice of the Kähler structure is really only a choice of a class. Okay, so it's really just a Kähler class. And if I'm interested in, but I want to stress that these symplectomorphisms that I'm getting, they don't respect J anymore. Okay, they only, if I have some symplectic construction, then they will preserve it, but you won't be able to preserve complex constructions. Yes, Phil? You seem, huh? Okay. Okay, so I think I'm not going to actually really get to Loenga pairs, but it's okay.
This argument will fail there because the Moser vector field will not fail.
It doesn't really fail.
This argument will not fail.
It's a modification of that argument works. It's essentially the same argument. So here there is no, so all of these guys, so this smooth complex affine varieties, there are restrictions of the symplectic form from here, and this is an exact symplectic form. The restriction is also an exact symplectic form. So the cohomology class is 0. So what do you call this invariant doesn't exist there; it vanishes. But indeed, there is the biggest potential problem is that when you run this Moser argument, there is some vector field which you need to be able to integrate. Yeah. Okay. So now some more examples. So Kähler structures on point blowups. Blowups. Okay. Sorry, my underline J omega Kähler. So you can also think about it as a complex manifold with a Hermitian structure. And you take a point in that complex manifold and blow it up as a complex submanifold. Okay, so you replace that point with its with some projective space of the directions coming into this vector, this point, complex directions. Okay, so do a complex blow up at a point. Okay, and then there's a statement that maybe a theorem, I don't know, proposition, maybe it's not really a theorem. There exists a Kähler structure, meaning not just the class, but actual Kähler structure, an actual form, which agrees on the blow-up. Right? So you get y tilde on y tilde, which agrees with the existing Kähler structure on y outside of the exceptional divisor. Okay, so what do we have? So we have y tilde, this goes to y. And what's happening here is you have this manifold, you have this point, and upstairs, instead of having this manifold, you now have this CP1, but everything else, there's a biholomorphism. Okay, so there's this pi here. If you remove this exceptional divisor and this point, it's a biholomorphism. So they're canonically identified. And there is a Kähler structure here. So what I'm saying is that you can find a Kähler structure here. It's a Kähler structure everywhere. And it also agrees outside of some neighborhood of this, some arbitrarily small neighborhood of this exceptional divisor. It agrees with the Kähler structure here. Okay, yeah, so this is an important statement. And maybe, okay, maybe I won't try to say that. And it's not just that, it's not just some existence statement. You can write a formula for this, okay? There is some undetermined, there is there is some quantity that you're trying to make positive. And it initially is negative, so you end up kind of having to fix something, having to change something, and you may not know exactly by how much you have to change. So there's something to doing this. Okay, so it's too much for me to explain it here. But you also have Kähler structures on blowups. Okay, I'll finish with this. This is the last thing. Sorry. I want to give you another example of getting not Kähler structures, but symplectic structures. So almost example. Okay, so this example is holomorphic symplectic manifolds. Okay, so what's a holomorphic symplectic manifold? It's a complex manifold with a holomorphic two form, which is closed and non-degenerate. Okay, an example, a sub-example, is if Y is a complex surface and omega is a holomorphic volume form. So, but it needs to be a surface, right? It's a four real dimensional thing. Okay. And because it's a holomorphic volume form, this is a two form, so it's actually a symplectic form. Surface and you have a holomorphic volume form on it. For example, if you have a Calabi-Yau surface, like a K3 surface or something like that, then you have this holomorphic symplectic structure. Okay. And then what you can do is you can multiply this omega with any phase, and you can take the imaginary part of this complex valued form, okay, for every theta in 0 to pi. And this is a symplectic form on Y bar. Okay, but it's not a Kähler form because it's not going to be compatible with the J. Okay, but maybe warning, not compatible with J. Okay, and maybe I'll just say this and not write it. Sorry, I'm over time, a penalty, sorry. But just one more thing. So a special examples of holomorphic symplectic manifolds come from hyperkähler manifolds. And if you have a hyperkähler manifold, then you don't have just one natural J, but you have this twisted family of J's. This P1 complex line family of J's. And if you do this there, then this will not be compatible with the J that you started with, but it will be compatible with some J that lives on that twister space. Okay, so it will be a Kähler structure for that J. Okay, I'm gonna stop here. Next time I'm gonna just start with Loenga case and tell you. But you can now kind of tell. You should be able to now think about how you might go about constructing Kähler structures on low Calabi-Yaus using their toric models. Okay, you start with Kähler structures in the toric case, and then you blow up and you use this, or you use their holomorphic volume form and take its phases and so on. Okay, so you can get symplectic structures this way. Okay, I'm done.
Okay, thank you. Okay, any questions for in this room? Physical room? Can I ask one? I don't know if it's stupid or not, but so if I have symplectic manifold, usually you can find all the complex structure, right?
Yeah, you can always find.
It doesn't matter which one you choose.
Yes.
Contractible family.
Yes.
So with Kähler, so it's symplectic manifold, you can also find a J, right? And there's an integral one.
Not always, no.
Oh, it's Kähler.
Oh, if you know that it's Kähler, okay, okay, oh, yes.
So
okay.
The J,
yeah.
More ways integrable, right?
Yeah. Is integrable J's contractible? Is your question?
Yeah. Or it doesn't matter.
I don't know. Does anyone know the answer? Yes, I don't. I would say probably no, but I don't know. I think so. I think so because so. Yeah, I don't think. I mean, this contractibility is really not. Yeah, I would guess no, but I don't know if there's a theorem, like a counterexample. Like,
yeah.
Huh? But do you have an example?
Like
Huh? Sorry?
A two-word surface or something like that, the moduli.
I couldn't understand.
Sorry, I mean just like a surface, some genus to surface or something like that. I think that should, like all the J's. Oh no, but then all J's are repeating. No, that's contractual. That's contractual.
I think we can think about this later. I just don't have a quick answer.